Hello and welcome back to Calculus 2, section 10.2, polar coordinates. All right. So what do we know? What do we need to know for this section? Well, hopefully values for sine of 30 degrees, sine of 60 degrees, tangent of 30 degrees, and so on. Well, we don't need tangent. Sine and cosine. If you haven't learned what those values are, I'm going to show you a very simple, straightforward way to construct the table of all values that you guys need to know for your future education. Now, this is something that you're supposed to have from pre-calc, but such is life, right? This is what we're going to do. We're going to create a table with sine, cosine. We don't need tangent for this class, but for the sake of completeness, I'll put it there. We're going to put important angles across the top: 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Now, some might have trouble with converting those into radian measures, which include pi. So you all know that 90 degrees is pi over 2. So you can go 2, 3, 4, skip 5, and then 6. One more time: 2, 3, 4, skip 5, 6. To convert them into their radian equivalent. Now, how do we construct a table of all values easily? Here's the trick. Look. You start with 0, and you write 0, 1, 2, 3, and 4. You divide everywhere by 4, and you take the square root. It's a very systematic way to obtain values. So 0, 1, 2, 3, 4, divide everywhere by 4, and take a square root. When you compute these, you are going to end up with values 0, half, root 2 over 2, root 3 over 2, and 1. Meaning that the sine of 45 degrees is root 2 over 2. Sine of 90 degrees is 1. So you can read in the chart sines and cosines of all of these values. Now, for the cosine, you will take same numbers and write them backwards. So you will start 0, and then 1 half, and then root 2 over 2, root 3 over 2, and 1. So for cosine, the same values, just written backwards. We all know that the tangent is sine divided by cosine, so you will simply divide these numbers. 0 divided by 1 is 1. 1 half divided by square root of 3 over 2 is square root of 3 over 3. Root 2 over 2 divided by itself is 1. Root 3 over 2 divided by a half is root 3. And undefined at the end, because we have a vertical asymptote at that place.
Isn't tangent supposed to be 0?
So tangent? Oh, tangent of 0 is, yeah, tangent of 0 is 0. Wow. 0 divided by 1 is 0. Wow. Thank you. So, when I used to teach at NGIT, I used to have a competition for my pre-calc students who can draw this chart the fastest. And usually I give an extra credit point for the test for the one who has the fastest time. So try to recreate the entire chart in 28 seconds.
I do the whole unit circle in 2 minutes and 7.
28 seconds for this chart.
That's just a chart. It's not even like you gotta go around in circles or...
All right.
Does it count if you already have the chart drawn?
No, blank sheet of paper, 28 seconds. So you have something to practice at home. So this is the chart of all the values, for trig. Now let's say that the question that you are facing is, what is the cosecant of 60 degrees? How do you find that? You do what?
Pi over 180, where you can convert it to convert it radians.
Well, we don't have to because we have a 60 degree in a chart, so we know. You can also say pi over 3, fine. But how do we compute this? What is the value?
Pi over 3. Sorry, it's going to be square root 3.
How do we calculate this? 1 over sine of 60. How much is sine of 60? So it is 2 over root 3, and then we rationalize 2 root 3 over 3. You can compute any trigonometric value this way, right? Now you can go and have the half angle formula, double angle formula, right? All of those guys to maybe work on a sine of 30 degrees, and right? But you have the most important values that actually show pretty much all the time. Anyway, so now that we have this prerequisite, we move on to the unit circle. The unit circle is circle of radius 1, and we can represent the angles by understanding that this is 0 degrees, 90 degrees, also known as pi over 2, then halfway is the 45 degrees, and then you have the 30 and the 60 degrees marks. Hopefully you immediately see that the positive angles will go as you go counterclockwise, and the negative angles will go if you go clockwise. So if you need to draw, let's say, negative 30 degrees, which is negative pi over 6, let's say graph, you will do a 30-degree angle below the x-axis, because that would be negative 30 degrees. Now that is equivalent to 330 positive degrees. So you can either have that or you can have this, which is clearly 11 pi over 6. Those two angles are the same location and two different representations for the same. Now each one of these can be periodically represented again and again and again and again by simply adding the period of 2 pi. So 11 pi over 6 has the same location as any, right? Well, I don't know, right word any, I'm going to put 11 pi over 6.
No, I meant where the... Oh, it's really hard.
7 pi over 6 is here.
No, I meant the... I can't read that. It's like...
11 pi over 6 over here.
Next to it.
This is pi over 6, and there is an arrow in front showing the angle going downwards. So I can represent every angle as the angle plus 2n pi, because you move the full circle. So that gives us representation of the same angle. So now when we have this trigonometric prerequisite discussion, we can dig into polar coordinates. Polar coordinates will operate also in xy coordinate plane, but they will act differently to get to the same location. So what you know so far is that if you have a point, let's say 4, 2, you will count 1, 2, 3, 4, and then 1, 2. So you will count 4, then you will count 2, and then the program would crash. And you will be able to get to the location where the point is. I'm going to do the thing on the side.
Wait, would you say it would go act in the same way in an XY plane, but they'll arrive in like a different location?
No. Let me see if this is... So, it seems that this is going to hold. Now I'm just going to restart. Make sure that... I've never seen this before. That's okay. All right. So here we go. So you know how to obtain this. This is 4 units. This is 2 units. So you technically count in a rectangle. These are called Cartesian coordinates, also known as rectangular coordinates. So this is rectangular coordinate because you can draw the rectangle and you can follow any 2 sides, right, 4 and 2, or you can go up 2 and then over 4. Either way, you're going to end up at the same location. Polar coordinates will do things differently. Polar coordinates are defined as r, theta. You have r for the radius and theta as an angle. So a typical representation would be 3 pi over 6, let's say. So the way you would do this is you will first draw the radius 3. Then you will locate the 30-degree angle, and you will swing this point onto that radius. This location here is 3 pi over 6. Step number 1, draw R on x-axis. If it's a negative number, you will draw on the negative side. So radius could be 5 or negative 5, 1/2 or negative 1/2, right? Can be any number. So you draw the radius, whether it's positive or negative, on the x-axis. And then you draw this construction line for the angle. So step number 2, draw the angle out like I did, the construction line pi over 6, which is 30 degrees. Again, positive or negative. You go clockwise or counterclockwise. And then, just in the arc, swing the point to the location where you need it. All right, so try this. Negative 4 pi over 3. Negative 4 pi over 3. a sec. Right? On whatever axis you draw your R, that's where you're measuring from for either pi over 6 or whatever angle. So now, we are going to draw 1, 2, 3, -4. Positive angles are counterclockwise, therefore I will start on the negative x-axis, draw a construction line for 60 degrees, and swing the point onto it. So there it is. Right there. This is still good old X and a Y graph. Let's try another one. How about 3 and -pi/4? All right, so we quickly draw XY. We go 1, 2, 3 on X, and we go down to pi/4 is the 45-degree line, right? Should hit through each one of these squares. And then we swing onto it. Now, when you are graphing this, nothing is important other than the point. It should just be, right? You should not have anything else other than, let me just see if I can erase this point now. Come on. Kill it. There we go. So nothing is important other than the point in on the graph, because this is just one point. All of these other lines that we draw are construction lines that help us find it. Earlier we were able to just count in each square, right? And there was little dots, so you're not that visible. Now with these extra lines, you know, it might seem like, you know, there's more going on.
I got a quick question. How can you tell your point is not off? And for instance, what happened if I drew it a little bit closer, negative pi, 7pi/4 towards like 7pi/3, to like pi, whatever it's called.
Well, you do the best you can. I mean, the first rule of engineering, if any one of you ever wants to be engineer, the first rule of engineering is draw big, so that those things don't get in your way. right, where something is not drawn to scale or not drawn proportionally or not, right? So technical drawing, you have classes for that, and you need to be able to create and read technical drawings, right, as engineers. So
For this case,
well, in this case, it's just practice and, you know, do as well as you can, but you know, a little bit of OCD helps along the way. That's the art. OCD is awesome. I love it. Right now, we have discussed what polar coordinates are. So polar coordinates give us radius and angle, and we now know how to locate the most basic object, which is a point in the space. Now, when I draw a point in space and get it using polar coordinates, anyone would argue that we can get to the same point using rectangular coordinates. And that's true. So there has to be a conversion between the two worlds. And that conversion is extremely important. Conversion, xy, back and forth, r theta. Now, I never liked memorizing too much, which is the reason why I stay away from organic chemistry and biology, unfortunately. So I'm not able to perform well in those particular disciplines. But anything else that adds formulas and derivations is extremely cheap and easy, like physics, general chemistry, any type of engineering, right? Because you have equations and it was simple. Now, I didn't even like to memorize those formulas. I like to see the way of how to derive it. So you can either remember both sets of formulas, or you can just remember one triangle and get it from that triangle every time you need it. Observe what's happening here. Say you draw a point using polar coordinates. So the polar coordinates to that point will have radius and angle theta. Right, that's the polar coordinate right there. But then you can also drop down, and that will be y, and this would be x. So you have a triangle, right triangle, that you can write 4 basic equations: sine, cosine, tangent, and Pythagorean theorem. Those 4 equations are 2 sets of 2, right? 2 sets of 2 that are converting one way or the other way. So if I write that sine theta is equal to opposite over hypotenuse, you can see that you can solve for y and get y is equal r sine theta. And if you write cosine theta as x over r, looking at the triangle, which is adjacent over hypotenuse, you have x equal r cosine theta. You already see that this pair is converting polar into rectangular, because both polars are given to you in each equation, right, r and theta, and you are computing x and a y one at a time. You can also write tangent theta as y over x, opposite over adjacent, from where you can solve for theta as the inverse tangent y over x. And you can also write x squared plus y squared equal r squared, which is your Pythagorean theorem, to get that r is square root of x squared plus y squared. I'm going to box these actually using the pink. The second one is clearly rectangular into polar, because both x and y are given in each of the equations, and you get the polar coordinates one by one from each equation. So, what I argue here is, just use common sense. I will repeat this one more time. First observe, if you don't want to memorize formulas, the triangle will give you all of these formulas quickly. Observe. Why are these polar to rectangular? Both polars are given, and you are calculating one of these at a time. Over here, both x and y are given, and you're calculating one at a time. So rectangular are given, you're getting polar one at a time. Over here, polar are given, and you're calculating rectangulars one at a time. So you can think of it that way. And now is the time to actually do the conversion. Say your point was 3 pi over 6. Clearly that's the polar world. We want to shift this into rectangular and see what we get. Rectangular is x comma y. Well, x is r cosine theta, which in our case is 3 cosine of pi over 6, which is 3 times root 3 over 2, which is 3 root 3 over 2. And the y is r sine theta, which is 3 sine pi over 6, 3 times a half, 3 halves. So the point 3 pi over 6 converts into 3 root 3 over 2, comma, 3 halves. How nice or easy is to graph this point in rectangular coordinates? Right? I understand that the second one is 1.5, right? Easy, right? But the first one with the root 3, not fun. And how easy is to graph this? Fairly easy, right? We'll see more of that. Let's convert another point. Let's even make it easy. How about point 512? Change into polar. You remember the formulas. R equals square root of x squared plus y squared. Theta equals inverse tangent of y over x. What do you get? So r is equal to square root of 5 squared plus 12 squared, which works out to be 13. And theta is the inverse tangent of 12 over 5, which is, we can use degrees. Make sure that you have degrees on the calculator. For the inverse tangent of 12 divided by 5. Approximately 67.4 degrees. So, I'm going to ask the same question like last time. Easy to graph in polar coordinates or no? Not easy, right? Look at that angle, 67.4 degrees, right? Is this easy to graph? Of course it is. This is the first glimpse of us realizing that these two coordinate systems are not in opposition to each other. They complement each other. What's easy in one is most likely going to be terrible in the other one. But we are yet to discover that when we look into the functions, which is the next topic. So now we are going to peek into functions in polar coordinates. So we are moving to pre-calculus portion, right? Function in polar coordinate has a form of r equals f of theta, which means theta is independent variable, and we know that the domain of theta can be restricted to, I don't know, pi over 2 to 3 pi over 2, or negative infinity in terms of pi to positive infinity, right? So domain, right, angles are input, and r is the output. You can get some really cool stuff when you are looking into functions in polar coordinates. Do you all have a graphing calculator TI-83 or 84 with you today? If not, you can bunch up with someone if you're interested in these things. Anyone? TI-83 or 84? Ready? Actually, I do have one extra calculator here. If you have a group of people who, so you're all good? Does anyone need a calculator? We have at least a pair. Each pair has a calculator, right? At least. All right. So this is what we're going to do. First, go into mode, and you will make sure that the calculator is in radians. Where are your calculator? Oh, I can't see. Oh, good. So you go into mode and make sure that your calculator is in radians, and then the line below when it says foot par pole sequent, right? You go into POL, polar.
More math I take, the more
Well, they can't name a fine.
All right, so polar.
Can't build fine.
So now you have radians and polar. That's what we need. Exit of that. Second quit. Back to the main screen. Push Y equal, and you will see that your screen there used to have F1, 2, 3 now has R because it's input. The first line will say 4 cosine 4, and when you push X variable button, it will print theta now. Now you see why that has XT theta n. Depends which mode calculator is in. And then hit enter and go to the next line and put 0.5, let's say, cosine of 10 theta.
Okay. Well, we don't understand what the first step was. Can you say a little bit slower? Man,
You don't do the same calculator, right?
No, I'm seeing inspired by, of course, I know the
It's not
equation.
the same. It's not the same, different steps. I don't know what the steps for that one are.
Okay.
All right, so now, guys, we have 4 cosine 4 theta on the first line, and 0.5 cosine 10 theta on the second line, right? Hit enter, second quit. We're gonna go into window, and in the window, make sure that the X window, X minimum -6, X minimum -6, X maximum 6, and then Y min and Y max -4 and 4. Don't change anything else. So x min, x max, negative 6 and 6. Y min, y max, negative 4 and 4.
And what was the second one again?
Second equation,
Yeah.
0.5 cosine 10 theta. Now, push the graph button.
Oh my god.
What did you get there?
What?
I might have done that.
Oh, that is a butterfly. All right, so fine. So he got a butterfly somehow, which I actually want to know how it's done. Oh, he's probably not the radius.
No, he is. He just typed in the wrong function.
Just remember that. I think that was theta.
Yeah, that was cool.
Yeah.
Oh, that's the 10 theta right there, and then the other one. Okay.
But you did get a butterfly. That's
You did.
very interesting. Yeah.
Bonus points.
So now see that. So now see the dozen flowers in a bouquet can cost $1,200, right?
Do not hand this calculator.
No, not I actually did take it to a date one time. It worked. It's like a phone. I
can also make you those
and then you erase. So the polar graphs are polar graphs. You are not used to polar graphs. So I hope that you will be using calculators extensively to visualize and learn which equation gives what and so on. Remember, you have what? 8 years of training of graphs in XY. Taking x squared, linear lines, and all of the other things, x cubed, sine, cosine, right? All of that stuff. You've been seeing it for 8 years, let's say, at least, right? This stuff, we haven't even spent 8 minutes yet. And it's completely different ballgame. So, use the calculator as much as you can. Use the online tools, right? Graph Polar, Wolfram, to visualize how these graphs look like. Now, I told you that theta is the input and r is the output of the function, right? Domain and range. And you've just seen that these functions give you, in this case, it was a flower, right? And what I used was r equals 4 cosine 4 theta. It gave you a flower with 8 petals. There are other shapes that you can discover through these, right? So to draw this, by hand, I guess we draw, and then in between. So it gives you something like this, obviously much nicer on a calculator than what I did. So now, I want to call your attention to the shape of the graph. Looking at it, forget about the r equation on the side. Just look at the graph. It's on the xy coordinate plane. Is it a function?
Yes.
Hell no, right? It fails vertical line test. It cannot be a function in our xy, right, Cartesian coordinates. But look at its equation in polar. A simple cosine equation. You can do anything with it. Now, I do want to convert this into xy and see what it is. So what do?
Going into the formula.
We use the formula. But you can't convert cosine of 4 theta. You can only convert the basic cosine, right? And sine. So now you have to figure out how to transform this, which is r equals 4 cosine squared 2 theta minus sine squared 2 theta. That was a double angle formula for cosine. You still have 2 thetas. Remember, your conversion formulas have a single sine, single cosine, so you have to do this one more time. R equals 4 times, and now this one needs to go down into a single theta, so that's going to be another cosine squared theta minus sine squared theta, everything squared, minus 2 sine theta cosine theta, everything squared, and everything times 4. So now that I'm down at basic sine and cosine, I can plug in what they are. But the problem is that I don't have what the sine is equal to and cosine is equal to. I have to use the inverse tangent in its place, right? There is an easier way, but let's see the horrors of this. So what's r?
4.
R is going to be square root of x squared plus y squared. Then we have 4 times cosine squared. So it's going to be cosine of tangent inverse of y over x, everything squared, minus sine of tangent inverse of y over x, everything squared, minus 2 times sine of tangent inverse y over x cosine tangent inverse y over x squared. Boom.
Still don't explain. You still don't explain where you got this. I mean, how do you get it? You can't.
You know the theta is tangent inverse. I just plug it in.
How do you get tangent inverse, man?
That's a formula. You have it on your conversion. Theta is tangent inverse y over x. Plug it there, plug it there, plug it there, plug it there. That's all I did. And replace r with what the formula for r is. So there you go. That equation is all in x and y, right? Now all we need to do is to make it y equals everything else. Can't do it, right? Can't be done. Now, you can simplify each one of these. You can simplify each one of these by simply doing the triangle, which you can actually get easier without all this mess. I just wanted to show you the general way of doing it. There's a much faster way of doing it by realizing that x equals r cosine theta. So cosine theta is x over r, right? So you can plug that there and then just replace r with this. It's much easier than having the stuff like this. However, and you can do that pretty much every time, this is what the function looks like when it's fully expanded. Sorry, it's not a function, it's a relation, right? Definitely not a function. You see the graph up there. So now, you have to understand that when you're looking at this mess over here and realizing that this is one equation that connects x and y, and these all things graph that, and as the alternative, that same equation is actually this. You want to work in that frame, in a framework where you have a simple representation for it. So sometimes, as you move on through your math career, it's easier to convert from rectangular into polar and deal with stuff. Now let's see what are the easiest equations, what the easiest equations represent. We know that easiest equations that you can draw in Cartesian system are x equals a number and y equals a number. So if you are looking in the rectangular system, you have x equals, let's say, 3. It's going to be a vertical line going through 3. Or, let's say y equals -2. It's going to be a line through -2. So for rectangular system, right, the easiest equations that you can draw are either a horizontal or vertical line. The easiest equations that you can get in a rectangular system are horizontal and vertical line. X equals a number, y equals a number. How about for polar? Well, clearly we have theta equals a number, so pick something like pi over 3. So what is this? Theta equal pi over 3 is going to be a linear line through the origin at pi over 3 angle, right? And that line is infinite, going up and down forever. And observe that all of these equations that we have right now on the screen, all three of them, they don't have a mention, like if you look at each equation individually, they don't have the mention of its other coordinate. X equals 3 doesn't mention y. Why? Because y takes all values from -infinity to +infinity. Y also doesn't mention x at all. It's drawn for all x. So theta equals pi over 3 is drawn for all r's. R is 0, R is 1, R is 1/12, right? So all of those. And we have one more. R equals, let's say, 5. What is that equation? R equals 5. Remember, you have to draw the radius of 5, and then you have to draw that for every single angle out there. What do you get?
You get a circle.
You get a circle. Very good. You get a circle. R equals 5 is a circle, a radius 5. Now, you know that circle is not a function, right? You know that you can't integrate. Then when you deal with the equation that has circle mentioned in some case, you have to do trig substitution, right? You know that the equation y equals 25 minus x squared, right, is a semicircle, and you have to do trig sub to solve that integral. Look at that equation in polar coordinates. R equals a number. That's how awesome and how easy polar coordinates make this. So I'm just going to actually go and say this is equivalent to writing x squared plus y squared equals 25. Not a function, can integrate, can do stuff easily. But in polar coordinates, we will be dealing with r equals 5 to represent the circle. Integration, a joke. Derivatives, we'll see about that. So the two basic equations, theta equals a number, is going to be a line through the origin at the angle that you are at the angle that you have, and then r equals a number, r equals, let's say, 5 in this case, is going to be a circle of the radius that r is equal to, right? So now that we understand two basic graphs, I would like to graph by hand one of these functions. And we are going to graph by middle school method. We are going to pick thetas, and then we are going to see what we get. So let's go with y equal, let's say, 3 sine 2 theta. Sorry, y, r equals 3 sine 2 theta. The way we're going to do this is we're going to pick thetas, calculate r's, and then have r comma theta point, and then we're going to graph to the right. Now, let's see what happens here. Pick thetas 0. Now, you can pick pi over 8, because pi over 8 times 2 is pi over 4, and you can compute that. So pi over 8 is okay. Then you have pi over 4, and then 3 pi over 8 is also okay, because you have pi over 8. Well, you can calculate all increments of pi over 8. That's the easiest to think about, because, as I said, you want to start with pi over 4, but because you are multiplying by 2, it's okay to start with pi over 8. And then you just go 1 pi over 8, 2 pi over 8, which cancels to pi over 4, 3 pi over 8, 4 pi over 8 cancels to pi over 2, 5 pi over 8, 6 pi over 8 is 3 pi over 4. I mean, it's already not getting long there, but we can do these things. Plug in 0. Sine of 0 is 0. Times 3 is still 0. To write r comma theta is 0, 0. It's the origin. Plug in pi over 8. We get sine of pi over 4, which is root 2 over 2. So 3 root 2 over 2. I'm actually going to convert those points using trig. Using a calculator. So 3 times root 2 divided by 2 is about 2.1. So 2.1 and pi over 8. When I plug in pi over 4, I get pi over 2. Pi over 2 is how much? Sine of pi over 2? 1. So I'm getting 3. So this is 3 and pi over 4. 3 pi over 8. Sine, positive in the second quadrant and all of that kind of stuff. We're going to have 3 root 2 over 2. So we're having, again, 2.1, 3 pi over 8. Sine of pi over 2 times 2 is sine of pi, which is 0. We're having another 0. Pi over 2. Let's say we had enough. The first point that we want to graph is 2.1, right there, and swing that pi over 8. Okay, so I'm going to draw construction lines for pi over 4, and then I need half of each one of those for pi over 8. Now I need to that's 2.1. So 2.1, 2.1, and then 3. Go from 0, hit the first point, go to the second point, go and go back. We got a pedal. Right there. the next stuff, which I did not compute, is going to give you a pedal over here. It's going to go across. It's going to go down. Bring it back. And you will have a 4-petal flower. Why 4? Because this is even, and for flowers, even number gets doubled, odd number stays the same. So sine of 3 theta has 3 petals. 5 theta, 5 petals. 11 theta, 11 petals. 12 theta, 24 petals. All right? So even numbers are doubling, and odd numbers stay what they are.
How you get to 0 and the guy could probably explain a little bit better, but how you get to 2.1 to 3 and everything like that.
2
And
point.
You said that the equation for r equals square root of x squared plus by y squared.
This is the equation for r.
Okay. And then
You plug angles in here.
How will you get the so then you would say you get 3 square root 2 over 2, but how you get 2.1?
Plug it that in a calculator. This is 2.1 in the calculator. So I can draw it. Make sense? So you just compute 3 times the root 2 divided by 2. So this is how you graph these things. And I want you to try and graph one of these. All right, let's try what do you want, 38 or 40? 38 or 40, quickly. 40 it is. Graph r equals 1 minus cosine theta. Do it the same way I did it, except now you have to pick nice values, right? Pi over 6 and all of those, because we don't have any number in front of theta.
Is it done? Yeah, just one left. That one. That one. If I grab it, I'm eating it. If I grab it, I'm eating it. Oh, you missed it. What did I miss? He's working on it, the last one. Ooh, nice. Now I want that and the bag. You can continue.
Yeah, for my final, I'll just bring in my pretzels in a jar of Nutella.
But you're yet to beat mine.
We're talking steak in the candle. What?
You did what to what?
When I was a student here, they just finished what is now known as the old wing of the science building. And the biggest classroom is 101, right? Was the computer lab. And there were signs every 5 inches saying no food, no drink, right? And we had this professor who was Muslim, and he observed Ramadan and other holidays, and he would not eat the whole day until the sun goes down, and he would bring the food, and then he'd teach and eat, as you all understood, because he didn't eat anything for 18 hours or 16 hours, right? And I said, well, you know, the rules are rules, and every time students are bringing a water bottle or something, everyone but him, any other professor or anyone else passes by would scream at them, like because it's brand new. So one day I decided to break the rule. I brought in a plate setting, a full plate, steak on it, potatoes, steak knife, and fork, old metal, right? Put the candle, salt and shake. Put everything aside. If you're breaking the rule, you're breaking in style. The lab assistant walked in. Charles in the pile, looked at it, and just walked away. Said nothing. I had a candle, the light goes on, salt and pepper shaker. The only thing that I didn't bring is a little, you know, music or something. On the side, that was the only thing that was missing. It would be so awesome.
I got a quick question.
And I had the wine bottle with the cranberry juice in it. It looked like it was that was, yeah.
The one I grabbed out looked like this, but of course I'm just wondering if this other side has to be filled in as well.
Well, that's only one.
Yeah. Do that, and it's going to go out.
Yeah, but so
So should I just like, I know they reflect this point. Now, because like I'm doing the reflective point, I mean, remember how you said
it's not going to be always symmetric. 1 over 1 minus cosine?
yes, 1 minus cosine. Like, for instance, 3 pi over 4 to
Crazy over there.
like this. But may I ask you, how many should upon graphing should we basically do 1 point from every quadrant?
No. No, we're not gonna graph by hand on a test. No. We're not gonna graph by hand on a test these polar coordinates, but it's just the skill in case that, you know.
No scientific calculus. There is no graphing calculus allowed on
Exactly.
So what about this? What about the graphing? What would you do?
Parametric, probably. That's you know, something that can be achieved. All right, guys. So here we have just you know, first quadrant points. Cosine of 0 is 1, and then 1 minus 1 is 0. So we have 0, 0. We start at the origin for our r theta. Pi over 6, cosine of pi over 6 is root 3 over 2. So we have 1 minus root 3 over 2, right? And that gives us something when you simplify. Pi over 4 is root 2 over 2, so 1 minus root 2 over 2. Again, something. Pi over 4. Pi over 3 is a half, so that gives us a half. That one's easy. And the last one is cosine is 0, so it's 1. As you graph this, let's say this is 1. You will get something that we call cardioid. Justin, you okay? It will create these two parts like this, and then go around, and it looks like a heart. This is called the cardioid. Now, what we did here in this chart is this much. That's all we graphed from the chart. If you go and you pick angles from the second quadrant, you will get this, the third quadrant, and then the fourth quadrant, right? So you have to, right? It takes time to graph these things by hand, which is the reason why I said that you guys should be using a graphing utility to kind of get the graphs. Now, in tomorrow's lecture on the calculus of these things, we're going to have a lot more to worry about graphing, because remember what we are doing with integration. We're looking for the areas, right? And areas can be tricky. Apparently, there is a beautiful butterfly graph that you can get. See that? And the equation for it is e to the sine theta minus 2 cosine 4 theta. If you plug that into the graphic calculator, you're going to get the butterfly. So these equations are really awesome. You should take a calculator and play, see when you adjust the number in front of theta on sine and cosine, if you subtract and add things, how that impacts the graph, and then just read the book, see what types of graphs are around, so that you can do this. So tomorrow, after the exam, we are going to go and do 10.3, which is calculus of polar coordinates, which means we are going to take derivatives and integrals. We're going to look for the area of the flower or cardioid and intersection between different shapes. Now those are very tricky because you are not used to the graphs. So you'll really have to pay attention on that one. And that will end the course. We'll probably, after the exam, there will be some stuff left over a little bit to take care of the Wednesday of that section. A few more examples, then Wednesday is the review. And exam is on, final exam is on Thursday. Let's say we'll start by 8 o'clock. So say 8 to 10 is the final. So exam tomorrow, review on Wednesday, final on Thursday, and don't forget the projects, don't forget any class preps, any homework, anything that you hand in on Thursday counts. And Thursday, when the class is over, the course is over. That's it. I will not be coming back to the campus till August 30th, I believe. And if you need to see your final exam, if you want to see your final exam, contact me. We'll make appointment sometimes in September or October. Whatever, you know, we can figure out the time. Generally during office hours. You can review the final exam if you're interested. Oh, actually, I forgot to say bye to the stream. They don't need to know.